Namaskar and welcome back to our series of lectures on infrastructure asset management in a course being offered under the Government of India initiative MOOCs. In our lecture today, we are going to focus on concepts in maintenance of infrastructure in light of the discussion that we have had earlier, which is primarily focused on the deterioration time and the performance time curves. A statutory kind of warning that this material being shared with you in the course is strictly for academic purposes and should not be used for any other purpose. And what you see on the screen is like the blackboard in the old fashioned way. Please make it a habit to make notes as usual using what is being projected and what is being stated. To recap what has been done so far, we have talked about the conduct of the course, which will be done as per the NPTEL or MOOCs guidelines, and we have tried to do an overview of the infrastructure asset management the way we look at it and we want to present it to you. That includes its life cycle, infrastructure involving massive initial investment and having a very long service life, the components being located in diverse environments and being subject to damage over time due to this exposure, and we have talked about concepts of deterioration and performance at the conceptual level. Moving forward in our discussion today, based on the belief that infrastructure asset managers need to know the basics of the processes at work that attack and cause deterioration, which in turn may affect performance, we would today start with a brief discussion on analysis and design. You will recall that this was left to you as a question as to what the difference between analysis and design is, and you are supposed to think about it. So, today I am going to present my view on that, and we will continue our discussion on the deterioration versus time curve that we have laid out in light of the maintenance processes. Now, coming to the first part of our discussion, which is analysis and design. If we look at a system which is under the action of some input, that system produces some output. Now, this output is related to the input that is applied and the system characteristics. Let us try to understand this with some examples. Here is a rectangular block of area A whose modulus of elasticity is E. There is a force P which is compressive in nature acting on this block. Now, in our formulation of input, system and output, we can look at this example as the input is P, the system characteristics are A and E, which necessarily define what this block is all about, and the output could be the stress or the strain in the system, which is a rectangular block. What really happens now is that the question for analysis would be, given P, A and E, what are the stresses and strains? So, given the input characteristics and the system characteristics, what are the output? From our preliminary understanding, we know that the compressive stress is basically sigma, which is P by A, and the corresponding strain, which is often denoted by epsilon, is sigma by E. We can replace the sigma by the P by A and so on and so forth. So, basically under the action of the load P, given the fact that the rectangular block has an area A and is made of a material which has a modulus of elasticity E, the response of the system would be a compressive stress of P by A and a corresponding strain of sigma by E. Now, from the point of view of design, what will be the question? Given P and an acceptable level of stress, let us call it sigma d, and or strain which is epsilon d, what should be the system characteristics A and E? In other words, we can say that sigma d and epsilon d can be treated as another set of independent parameters. Please remember that sigma d and epsilon d are not system characteristics. The system characteristics are still A and E, that is what we have to determine. Given that we have a P and these acceptable limits. We move forward and use the results from the analysis side, which is the stress, which is sigma, which is P by A, and the strain epsilon, which is sigma by E. What we have to do is to find the A and E such that this sigma that we get here and this epsilon that we get here is within permissible limits. That is, the sigma that we get should not exceed the sigma d. Similarly, the epsilon that we get should not exceed the epsilon d. Now, that is the design exercise. Now, this choice of the area and E, which is the material of that block, could be governed by considerations such as economy, availability, sustainability, and so on. And that is the starting point of engineering. So, engineering design incorporates concepts in economy, availability, sustainability, and so on and so forth, using the fundamental principles of analysis. Let us take another example. As a civil engineer, I am very fond of this example. We have a simply supported rectangular beam B by D, that is the cross section, this is B and this is D. B is the breadth of the beam, D is the depth of the beam. It has a uniformly distributed load. This is what we call a uniformly distributed load. Sometimes we have concentrated loads, but that is not what we are talking about here. We are talking of uniformly distributed load over the span L. This distance between the two supports is the span L, made from a material whose modulus of elasticity is again known to be E. Now, coming to the analysis. From our understanding of flexural behavior, we know that given the load L, B and D and E. So, L, B, D, E, these are all given parameters, given values, given numbers. We can determine tensile or compressive stresses, shear stresses and strains in different parts of the beam. Obviously, the stresses and strains in this part and this part will not be the same. Similarly, in this part here and on the top here will not be the same, and so on and so forth. Moving forward, we can find the deflection of the beam, that is, under this action of loads, will the beam bend, will it become something like this, and how much will this deflection be. So, these are the kind of things that analysis will tell us, that given the load, which is an input parameter, the span is an input parameter, these three are material parameters and the geometry of the beam that we have chosen. Based on this, the tensile or compressive stresses and strains in different parts of the beam and the deflection, these are the output parameters. From the design perspective, the question would be, we choose the B, D and E, that is the geometry of the beam and the material of the beam, such that the stresses, the strains and the deflections are within acceptable limits. One thing I am leaving out, can we easily change L, that is the span of the beam. The issue of L requires a little more thought from an engineering perspective. Why is it so is something which I am leaving out to you to think about. What could be the issues with L that are being alluded here? I will try to answer this question in perhaps the next class or maybe in the class after that. For the time being, the emphasis or the focus is that given a system here, which is a beam under the action of loads, how do we calculate the deflections, how do we calculate the stresses and strains? That is a part of analysis, and if we fix acceptable limits to the compressive stress or the compressive strain and the deflection, then what should be the value of B, what should be the value of D and what should be the value of E. Oftentimes the material is more or less fixed. We talk of a concrete beam, it could be a steel beam. So, we know the properties, that is E is known, and what we are really looking at is playing around with B and T. What is the geometry of the beam, or what should be the geometry of the beam, what should be the breadth and what should be the depth. So, that is what is the design part of it. I am leaving it to you to think of other examples of simple systems and look at them from the perspective of analysis and design, and be convinced that analysis is a scientific exercise where we try to get the output based on scientific principles. Design is also a scientific exercise, but the question is there are independently given parameters of acceptability. How much deflection in this case, for example, we accept, how much stress do we accept for a particular material. If we have steel, we have a certain number. If we have concrete, we have a certain other number, and so on and so forth. Try to think of different systems and better understand the difference between analysis and design. How this understanding will help us, we will try to see later when we try to examine more complex systems and take actual examples of things like repair, rehabilitation, and so on. Now, before we close the discussion on analysis and design, let us consider a reinforced concrete beam, which is also called an RC beam. In an RC beam, we have the breadth and depth of the concrete beam, and we have the overall depth here, and this depth is only up to the level of the reinforcement. The amount of reinforcement is AS, that is the amount of steel that we have put into the system. We often define a parameter called P, which is the reinforcement ratio, which is the area of steel divided by the effective cross sectional area. Note here that we are using small d and not capital D, and so on, and this beam, like the previous situation, is under the action of a uniformly distributed load, and the span is the same L. Now, in the design process, how do we determine this load? What should be the load that we take? For that, we have well established codes. Those codes tell us that for a particular type of beam, if it is a bridge, what kind of loading do we take? If it is a building on a beam, what kind of loads will be taken? So, those are coming from codes. These are called design loads. Then in the design process, for the chosen materials, we have to determine the cross section and the reinforcement level to ensure compliance with the maximum acceptable permitted deflections and stresses and strains. That is, instead of only B and D or this overall depth, we have also to determine the amount of steel. So, that is what becomes another system characteristics. So, this system of the reinforced concrete beam has properties in terms of breadth, effective depth, total depth, and the area of steel, and the system also has the characteristic of the span L, which we talked about briefly last time, and we have the load, which is given to us as an independent parameter. So, the question for design would be, how do we determine B, D and AS, so that the deflections, the stresses and strains are within acceptable limits. Now, the questions are, how are concepts like location, importance of the structure and the cost of failure taken into account in this design process? Similarly, do design loads consider variations of loads with time? Now, this time can be looked upon at two levels. One is what I can call short term. For example, if it is a bridge, for a certain time there is a train on the bridge, that is the beams and so on are under the action of the dead loads, that is the weight of the slabs and all that, which is all the time there, and at times there is the train on it and at times the train is not there. In the long term, there could be an earthquake, there could be a cyclone. Now, under those conditions, there is a different kind of load that is acting. So, when we are talking of variations of loads with time, we need to consider both these loads, and that is what is talked about in these codes as to how these loads should be incorporated in the design process. There are methods by which concepts such as importance of structure, cost of failure and the location of the bridge. The location could be one or another. One location could have more strategic importance than another location, and so on. So, how do we account for such qualitative information? There is a word which we call factor of safety. Now, we are going to talk about this factor of safety in a slightly different way at some point in time. But suffice to understand here that analysis is based on a certain load level. The design is based on a load which is determined based on the codal provisions. So, with this backdrop, let me move to the last element here, which is, do we consider in the design process the fact that properties of the material can vary with time. That is, if you go back to that old example where we talked about a block of material which has an area A and a modulus of elasticity E, can this area change with time? Can this modulus of elasticity change with time? In that case, how does our design process get modified? So, in the design process, in fact, even in the analysis process, when we use the A, that is, we try to determine sigma is equal to P by A. Now, the variation of P is given in the codes, and then you take a design load and decide something. What about A? If this A changes over the 50 years or 100 years that the bridge or the block is under operation, then the sigma will have a different kind of variations compared to a situation where the A is taken to be invariant. Similarly, the strains will have a different kind of variations if we assume that the E, that is the property of the material, also changes over time. So, these are the kind of things that an asset manager should have clarity of thought on. That is, what are the kind of things that are accounted for in the design process? What is accounted for in the design process and how it is accounted for in that design process? This understanding is very important when we try to inspect, evaluate and manage or maintain any given structure. From this point onwards, we will take a quick look at the slides which we had seen last time and then put them in perspective for our discussion today. So, here is a deterioration versus time graph, and the curve is characterized by an initial level of deterioration and a slope which represents the rate of deterioration. As far as performance is concerned, there is an initial level of performance which degrades over a period of time, and the slope of this performance time graph gives us the rate of change of performance. We wanted to understand the concept of service life in this framework, and what we did was, in the performance paradigm, we said that okay, here is my performance time graph, there is a critical level of performance, and then we said that service life can be defined as that duration of time till which the performance is higher than this critical performance level. The service life ceases when the performance falls below the critical performance level. The question of creating this using the deterioration curve had been left to you, and the answer is something like this, that is, we can define a critical deterioration level and then talk in terms of service life as that time duration where this critical deterioration level is reached. At times such as this, the deterioration levels are lower than this critical deterioration level, and beyond this point the deterioration levels are higher than this critical deterioration level, and that is unacceptable. We had also talked about the fact that the service life is an independently given parameter. We want to design a bridge or a dam or a road for being able to serve us for 50 years or 100 years or 70 years or whatever that number is. We need to have this curve and the critical deterioration level or the similar performance time graph and a critical performance level, and ensure that during those 50 years or 70 years or 100 years, the critical deterioration level is not reached, the critical performance level is not breached. That is the kind of thought process that we need to have in a comprehensive understanding of infrastructure asset management. Now, if we combine the deterioration and performance and look at it over time, we will have a graph like this, that is, the critical deterioration will be given on the deterioration graph and the critical performance will be given on the performance graph. So, a quantitative discussion on the basis of these qualitative schematic representations requires the tools and mathematical models for estimating initial levels of performance and deterioration and the rates of change in performance and deterioration, and this requires that we understand each deterioration mechanism, the local environment and the system characteristics and how they change over time. This information is very critical, and that is what we will do when we take up specific examples of structures in different environments and try to say that okay, this was an overarching paradigm or a framework within which in a particular situation how we will interpret the deterioration, how will we interpret performance. If required, we may have independent criteria for critical deterioration and critical performance. We already know that the rate of deterioration is essentially determined by the severity of the environmental conditions and the internal ability of concrete to resist that deterioration, and while designing, engineers try to work with models of the environment where the structure is located and impart enough internal strength to the concrete to withstand the environmental forces. So, all this we have covered last time also. And finally, each of the environments that the structures are in needs to be appropriately characterized, and the relevant properties of the concrete need to be modeled, and once this is available, then we can develop models for deterioration and changes in performance given a certain load. Moving onwards, the question is, why does performance change over time? Why do we want to monitor performance? We want to monitor performance because of these two primary reasons. One is we want to make sure that the facility continues to perform satisfactorily, that is, the performance is at a level which is acceptable. So, we have already got a critical performance level and we do not want to allow the performance to fall below that level, and we want to monitor the performance to make sure that there is no change in the performance level, or if there is a change, how much is the change. So, with these two principal objectives, we need to have inspections, and let me also add periodic inspections to get information about these two aspects. Though the principles we will go through are applicable to all infrastructure, for our illustration, we will largely focus and confine ourselves to concrete structures, which is a very important material used in infrastructure projects. So, let us move forward and try to understand the causes for repair and or reinforcement action. Now, look at this beam once again. Over a period of time, there can be increase in the load level, which means that the initial design, which was for a certain load level, let us say W1, and if the load changes to W2, then the design is not valid. Similarly, there can be a decrease in the load carrying capacity, that is changes in the material characteristics, that is your E, your A, your P, which is the reinforcement ratio. These things might have changed. There may be cracks that has developed in the concrete beam or the column or any structural system, and that has caused inherent weakness to develop over a period of time. And lastly, there could be a change in the acceptable response. For example, at some point in time t1, you accepted that L by 250 is an acceptable deflection in the beam. Come t is equal to t2, which could be 50 years later, the codes which told us that L by 250 was acceptable, the same codes tell us that L by 500 will be acceptable and not 250. Therefore, in all these three cases, whatever design we had done at time t is equal to t1, that design is no longer valid. These structures are no longer safe, if you want to use that word, and they all need to be updated. It is very easy, for example, in the case of cars, where they say that okay, at a particular point in time a certain emission standard is acceptable. 20 years down the line, there is a change in the acceptable standards for cars, and we say that we will not allow the cars which do not comply with the latest standards to operate. The question is, can we say the same thing as far as infrastructure is concerned? The important thing to understand is that the asset manager needs to know that okay, here is this basket of my assets which are outdated, that is they require some action. Here is the set of structures which were built after this time t is equal to t2 or whatever the time is, and this is more compliant. This question or this approach helps the manager allocate resources to repair and rehabilitation of structures. You have to have an understanding of what structures were made or what kind of infrastructure was built, whether it is bridges or roads or buildings or whatever it is, with what standards. That is why it is very, very important for us to archive information, archive details of design. What were the design codes used? What were the kind of specifications in those design codes? Now, let us look at a conceptual framework for maintenance of concrete structures with this backdrop. It shows that you start with an initial inspection and carry out a periodic inspection, do an evaluation at each step at the end of periodic inspection, and if required a detailed inspection, and at each step if we decide that nothing else needs to be done, then we simply close the inspection exercise. Else we proceed to repair, reinforce and so on and so forth. Please also understand that whether it is initial inspection or it is periodic inspection or it is detailed inspection, the issue at hand is really the menu, that is the items which will be studied, that is what will be the tests, what will be the methods used to collect data which will help us plot where that structure is on the deterioration time graph or the performance time graph. Visual inspection is a very important part of inspection procedures, but at times there are other methods available, non-destructive testing, core sampling and so on as far as concrete structures are concerned. But these methods using these techniques has financial implications, makes it more difficult, and therefore, it should be sparingly used. Having said that, they must be used as and when required. It cannot be a compromise. The other side of it is what should be the periodicity of periodic inspections, detailed inspections and so on. This discussion is very closely related to the kind of health checkups that we have periodically. At times it could be simple tests, at times it could be more detailed tests. The decision of whether or not to go for more detailed tests depends on periodicity that we have decided or the results of the simpler tests. Let us try to formally define some of these terms. Inspection is a generic term for actions taken to understand the current state of a structure. Repair is a maintenance measures to restore or improve the durability of a structure and reduce the hazards to the third parties. Strengthening is maintenance measures to restore or improve the structural performance such as load carrying capacity and or the stiffness of a structure or improve any other functionality that we may have. Serviceability restoration, functionality improvement and appearance improvement are other terms that can be appropriately defined. Let us take a more detailed or a closer look at the whole idea of inspection. We have talked about initial inspections, periodic inspections and detailed inspections. Initial inspections typically are undertaken before the structure is going into service. That is at the end of the construction process and at the time of handing it over to the client for operations. What is this other types of inspection? These could arise at the end of an event, and that is something which we are going to talk about later on today. Then there is an issue of method of inspection, which is basically the kind of tests that are going to be carried out. That is what I call the menu card. What should be the tests carried out, whether it should be, if it was a concrete structure, whether it was only Schmidt-Hammer kind of rebound tests or ultrasonic pulse velocities and so on and so forth. There are different tests. What is the frequency of inspection? The regular inspections could be carried out every month. Detailed inspections could be carried out as and when required or at least every year. The decision about the content of the method of inspection and the frequency of inspection is left to agencies who own infrastructure. That is, for example, the railways will have their own manuals which lay down the methods of inspection and the frequency of inspection of their infrastructure, which could be the rail, which could be their locomotives, which could be their buildings. So, for all these infrastructure elements, the railways will have an SOP which defines the method of inspection and the frequency of inspection. I am sure you understand that the kind of inspection that is required for a rail, that is the tracks, is very different from the kind of inspection which will be required for a locomotive or a building. So, that is where the test to be carried out is to be decided by the agencies. If instead of railways we are talking of highways, where we are talking primarily of roads, then again we have bridges, we have the roads, we have signages. So, all these elements need to be periodically inspected and there are different checklists for it. Moving forward, as far as initial inspections are concerned, we could talk of concrete used and the method would be documents. At the time of initial inspection, we are talking of inspection of a structure which could have been built over a period of 5 years. There need to be documents which have been appropriately archived, which tell us values such as water cement ratio, the cement type, the strength of concrete, the kind of reinforcement used and so on and so forth in different parts of the structure. We need to understand what is the cover which has been provided using the documents and some kind of field investigations. Now, this field inspection at the time of closure of construction and at the time of the structure going into service will help us understand what is actually the situation as far as the structure is concerned at t is equal to 0. That is actually what will help us determine the initial defects and get the initial condition. This is what was alluded to when we talked of an initial level of deterioration. It is not really deterioration, it is to understand that what was the initial starting point after which the structure undergoes deterioration. It should not happen that at 5 years we find some cracks somewhere and there is some kind of a discussion, no, these cracks were there initially also. We should be very clear that initially there were no cracks, or if there are cracks, yes, there were cracks. It was decided that these cracks are not harming the structure, they are within permissible limits and so on and so forth, and therefore, they have not appeared during the time that the first detailed inspection or the first periodic inspection takes place. The results of this inspection, as I said, are vital to establish the initial level of deterioration and of performance that we talked about in our earlier discussion. Coming to periodic inspection, they are carried out mostly by the owner of the facility, that is what I talked about railways and highways. Visual inspection is a very important component. Frequency of inspection depends on the environment and importance of the structure. For periodic inspection, it is very important the format of filing a report is predetermined and is able to follow changes over time. The format of the report or the checklist used during periodic inspection should not be subjective. It should not depend on the inspector, because these inspectors are likely to change over the service life of the structure. So, those inspectors need to have a certain format which is going to be used. Some things can be added to that format as technology progresses more and other tests become available. At that time it can be said that okay, these tests were carried out till 40 years, but after 40 years we also have information for this particular parameter, which could be a deterioration parameter or it could be a performance parameter. The inspection should be carried out with the intention to identify likely mechanisms of deterioration. It is not really identify in the true sense of the word, because half the time we understand or we know what kind of deterioration mechanisms will be operating, but we should keep our eyes and ears open to see if something else is not developing in the structure. That should be the aim of carrying out periodic inspections. When it comes to detailed inspections, as the name suggests, these could involve a more detailed investigation using more parameters. It could be strength, cracking, chemical analysis and so on. For example, chemical analysis of concrete need not be a part of periodic inspections, and only in certain cases it may be carried out under detailed investigation. And another aspect of detailed inspections could be collecting data from a larger number of points from the structure to choose parameters representative of performance. We must remember that as far as infrastructure is concerned, whether it is a bridge or a road or whatever it is, these are large structures. They have a span, they have a large spread, and therefore, if we have a road which runs into 100 kilometers, how do we sample? If we sample here, here and here, let us say 30 kilometers apart, is that sufficient? Somebody will say no. If we want to sample too many points here, then whether it is detailed inspection, whether it is periodic inspections, that becomes so much more time consuming and it is so much more expensive. So, this frequency and the amount of data to be collected, that is related to what is the kind of results we get, what is the importance of the structure, and again this is also a part of the SOP that different agencies have. The SOPs of course can be changed over time. It may happen that at a certain point the agency may decide that what we were doing every 5 years needs to be done every 3 years, or it may decide that well, it is enough to do it every 10 years because certain other things are being now done. All those options are available provided we have a clear objective thought process. And now coming to the thought process, the basic exercise through inspection, what do we want to achieve? We want to achieve studying a certain parameter representative of performance or deterioration. Here is our deterioration performance time graph. In this case, we are talking of performance which is reducing over a period of time, and we have A, B and C are successive points for periodic inspections. Now, what we should be really doing is estimate the level and the rate of deterioration at each point. That is, at this point in time, let us say A, what our objective should be that okay, how much is this deterioration, how much is this change in performance from here to here. Similarly, in B, what is this, and in case of C, what is this change. The other part of it is what is the slope here, what is the slope here and what is the slope here. We need to identify parameters which will help us get this information in terms of the extent of change in performance and the rate of change of performance. We should try to estimate the level of performance at the next point. That is, once we have information about the rate of deterioration and the level at this point, we need to estimate the level of performance at the next point. That is, if we have a situation that we have information up to this point as far as A is concerned, then we say that okay, here is the amount of change that has already happened and this is the rate at which this graph is going. And then we say that at B, which is let us say next year or after 5 years or whatever it is, this should be the estimated level of change. That is, from here this additional deterioration, if this was a deterioration time graph, this additional deterioration is likely to happen. When it comes to the inspection at B, we need to compare the actual value at B. It may be here, it may be here. If it is here, what is the conclusion that we draw? If it is here, what is the conclusion that we draw? And this was a deterioration versus time graph. What the conclusion is, if it is here, let us say x, which is lower than the expected level of deterioration at point B, x is lower than this. What does it tell us? It tells us that we overestimated the extent of deterioration. The graph is not moving here, the graph is moving more slowly. But if it is here, then our initial estimates of rate were not correct. And this needs to be carried out at B again for C. Assuming in all our discussion that the critical performance level or the critical deterioration level is far away. The problem will arise if the critical deterioration levels are close by, and that is where we need to be more careful. For example, a situation something like this, that if we have a situation where at this point we predict that if this slope continues, we will hit the critical performance level in this time itself, and we do not want to do that. Then what we need to do is to take an action which would basically reduce this rate of deterioration to a slower rate, and we get an extended time, because for the same critical performance level, if instead of this graph it goes on this graph, then critical performance level will be reached here and not here. So, this is the kind of thought process that we need to have in our strategies for infrastructure maintenance. Remember here that as far as our action is concerned, we have only tried to change the rate of deterioration. We have not tried to do anything to increase the performance level. It can happen that we want to do some upgradation. That means my action here includes upgradation that can be undertaken at any point in time and may vary in scale. That is, upgradation can be here, it can take you here, it can take you somewhere here. That is something which we can take a call on. Also, the post action deterioration rate, which is this graph has been drawn, this slope and this slope has been taken to be more or less the same, but it need not be. If based on this upgradation and this action that we have taken, the slope was also more gradual, that is, this is deteriorating at a lower rate than what we were having here, then we will get a further increase in our service life. So, obviously, these actions, whether we want to increase this, whether we want to handle the slope in one way or another, has financial implications. Okay, how much money do we want to spend in order to get this extension in service life? I am sure with these two examples of actions taken to handle only the slope of deterioration at a particular point in time and doing an upgradation at a certain point in time and doing a slope correction as far as deterioration of performance curves is concerned, this discussion that we had earlier, that is, we need to have repair or reinforcement action because any of these things, increase in load level, decrease in the load carrying capacity or change in acceptable responses. In any of these three cases, we need to have action which will help us make those structures more compliant with the prevailing standards. Now, so far we have talked about gradual changes in our system. Before we conclude the discussion today, I would like to add a disclaimer to our discussion so far. We had alluded to events, post-event inspection. Now, what is an event? One event that we can talk about is an earthquake. It is not a load which acts all the time, but it is a very, very important and a very severe load that at some point in certain structures depending on their location. Not all locations are equally earthquake prone. Similarly, there is fire. Engineers are aware that certain structures are more vulnerable to fire than others. There are methods and tools available for classification of structures for different types of fires. How do we incorporate this in the kind of management process that we have talked about? Earthquakes and fires are events that affect the performance of infrastructure, whereas we have so far confined ourselves to mechanisms or processes that gradually change the properties of the system. As the properties of the system change, the loads, whether it is earthquake or fire, can affect those systems differently. Now, that is what takes us to the concept of resilience. What does that mean? We have talked about performance versus time graph in this manner, where the structure is undergoing a gradual change in the performance. For example, now there is an event which leads to a sudden decrement in the performance level, and this decrement or this event depends on the magnitude or the severity of the event that hit it, whether it was an earthquake or it was a fire. The second part of it is how soon does the structure recover. Now, this recovery, there are two aspects to it. One is the rate at which it recovers, and the second part of it is where does it go. Does it exceed the initial level? Does it exceed this level, or it gets stuck somewhere here, and so on. So, that will depend on what kind of action we take in order to repair this structure. Beyond this point, again the same discussion continues. That is, whether we took it here, whether we took it here, whether we took it here, from that point onwards again this structure is subject to normal environmental loads, and again the gradual process of deterioration continues. The questions that engineers need to understand and answer is, by how much does the performance drop, how quickly does the structure or the system recover, and what is the post recovery performance time graph. So, if we are able to get this information, what we are doing is trying to talk about resilience. Now, as far as these three questions are concerned, we need to understand related to where we are on the performance time graph when the event occurs. For example, if an event strikes here versus the same event striking here, at this point in time the structure is weaker than it was here, the impact that it takes here may be different. So, this delta and this delta need not be the same. So, the same event can impact the infrastructure a lot more if it is already older, and that is why we have to understand the basket of our infrastructure. What is our infrastructure? How old is our infrastructure? What is the scale or size of that event, and what kind of remedial action is taken? So, all these things help us move in a direction, and what is the remedial action taken. Now, here are some of the questions that I am leaving for you to think about. We will probably talk about it at a later point in this course, where we are talking of this concept of resilience in more detail. Can a concept of consequence of failure be integrated into this thought process? For the recovery part, can there be a minimum required rapid recovery followed by a gradual full recovery? Now, let me give you a hint as far as thinking about this process is concerned. Think of a hurricane. That hurricane induces damage to essential lifeline such as power, gas, water and so on. It could be disruption in communications or transportation network. The question in all these cases, is there a minimum level where we must restore power, gas, water, communication, transportation, and then we can work towards a more gradual full recovery. Of course, this is preceded by trying to handle any injuries, any express damage that we see and so on and so forth. We have a different line of thought as far as a comprehensive understanding of this performance time graph is concerned. So, as far as this course on infrastructure asset management is concerned, the bottom line or the central thought process is a deterioration time graph or a performance time graph, and what we are trying to do is look at those graphs, have critical levels and see how we can handle different situations. So, with this we come to an end of our discussion today. I will share with you a list of references or material for further reading, which will help you understand the subject matter covered today and being covered in this entire course. And I would like to thank all my teachers and students who have contributed to my understanding of infrastructure creation and maintenance, and of course, some of these slides that I have used has permissions from some of my colleagues and I am indebted to them. Thank you.